Okay. In the third example, we will focus on the nonlinear curve fitting. We need to import the numpy as mp, import matplotlib pyplot as plt, from cgpy dot optimize import curve fit. Okay. What's the definition of the nonlinear model or the function? We should define the nonlinear model in here. X, Y is the collective data, A, B and C are the parameters, x1 and x2 is the R data, and return A times x1, but in this case we have the square form, or the over 2 must be added in here, and B x2 over 2 plus C. Okay, this is the nonlinear representation, but if we remove this squared form in here, or the over form in here, and then we have the linear model. Okay, so we should define again the generate synthetic data, mp random seed 0, and x1 data, mp linspace 0, 5 and 100, and x2 is written as the 3. This is our general presentation, and x1 and x2 data can be obtained with the mesh grid form in here, like this one, x1 data and x2 data, because it must be relation or build the relation of the x1 and x2 with each other in here, and we should assign the true parameters in here, like this one. For example, the 0.5, 0.8 and 1.0. okay, and y data is the R true data. Nonlinear model, x1 data and x2 data must be given as a tuple values, and true params should be given in here, but we should also add the 0.5 mp random function in here. For example, the rand n is the 100 times 100 matrix in here. Okay, these are noises values, just like in the sensor. Okay, as always we do, we should flatten the whole data. x1 flat, x1 data dot flatten, and x2 flat, x2 data, because we have the 100 times 100 matrices in here, like this one, and the y flat is assigned the y data dot flat. Okay, so the optimization or curve fitting in non-linear model can be done with the firstly initial guess must be assigned in here, like this one, for example 0.2, 0.1 and 0.1 in this case, and we should apply the params, and covariance must be obtained in here because we have the two-dimensional data, and curve fit must be given in the nonlinear model, x1 flat, x2 flat and y flat, and the potential initial gas can be given in the initial gas. Okay, so a fit and C fit can be obtained with the params. After that we can print the whole parameters in here. The params is the params. Okay, and so If I run this code, and then we will have the 0.5, 0.8, and it's approximately in what the 1 values in here. It's closest to the what the true params. Okay. True params, and the true params can be given in here like this one, and so this closes to the each other. Okay. So how can we create the what y fit model? Nonlinear model can be used in here like this one: x1 data, x2 data, and a fit, b fit, and c fit must be given in this case. Okay. After that, we should calculate the mean squared error of these terms like this one: y data minus y fit over 3. Okay. And after that, we should create the same plot like before, and so we should give the what the y data, true 2D data, the fitted data, and residual data. Okay. So if I rerun this code, and then we will have this nomination, but in this case we have the higher residuals value in here because it's a nonlinear model, and so the nonlinear model cannot be predicted or the modeled by using the some specific functions, because its nature cannot do that or cannot permit this representation. Okay. In the linear model, we can terminate or translate all the values into the y values because it's linear, but in the nonlinear form we have the some roots or the unmodeled dynamics. Okay. But if this is the case, we have the some noises value, but in our model we don't have any noise because we cannot model the noise value in here. But the range of these terms in here up to 20, and then we have the highest error in the 1.5. It's good. It's kind of the 35% error is given in here or happening in this case. Okay. So we cannot use this formulation to the nonlinear formulations of the R data representation. Okay. In the last case, we create the dynamic system fitting. Okay. For example, in your mechatronic application or in system dynamics or the control theory, we have some kind of x dot times ax plus bu. These are the general representation of any mechatronic system in the mathematical formulations. Okay, but if we don't have any knowledge about the a and b matches, or we don't know the coefficients of the a and b, how can we create the model, or how can we obtain a and b for a given dataset or the measurements? In this case, we will try to do that. Okay, so import numpy as mp and import matplot pyplot as plt should be given in here. We should generate the synthetic data in here. mp random seed must be initialized with the 0. Time steps should be defined in here like this one, 100 seconds in here. dt sampling period is the 0.1, and a true can be defined as the mp array. Okay. Firstly, we should give the some formulation in here, 0.5 and 2 and 0.8, 0.1. Okay, just like this termination, we shall give this mp array as the form of these terms. Okay. And also we should give this one, but in this case we have the 0.3 and 0.2. It's the B true matrix or true parameters. Okay. And so how can we emulate this system? mp zeros Q and time steps should be assigned in here, like this one. We have the 100 values and 100 times dt, which means that we have the 10 seconds value in here. Okay, and U must also be created with what the full of the what the 1 and the values of these terms 10. Okay, and so we have 100 data in the input value U value with the values of the what the 10. Okay, so how can we create these terms? T in a range of 1 and time steps, which means that we have the 100 iteration in here, and so we have the xt in here like this one, and p dot is the scalar dot operation, the dot product of the what the two arrays in here. For example, a true and x, the previous values must be fitted in here like this one, and we should give also to the what the mp dot and v true and u must be provided in here. Okay, so these are the system, these are the representation. This is the solution of the dynamic system. Using iteration. Okay, so organize the whole the data again. X past values can be assigned x minus 1. X next values can be assigned with the what 1 and the whole data, and u is assigned with the what the u minus 1 in a reverse order. Okay, firstly we need to apply the least square approximation in here, or the regression, to estimate a and b. Firstly we need to create a stacked structure in here, mp we stacked for the what the x past and u, because we should utilize the what the past values to the what to generate the next values in the time domain application. Just remember that up to now in this nonlinear fitting or the linear fitting parameters we have the 1 and 1 implementation, but in dynamic system we always create what the next iteration or the next values, and so this least square algorithm must contain this information, and so this organization of the data provide this feature. We should use what the x past and u to generate the x next values. Okay, and so AB estimate and residuals and some not used parameters must be obtained lin alg algorithm and LSTSQ algorithm. This is the linear programming or the linear algorithm in here. The linear algebra can be used in what to optimize the system, but which kind of algorithm must be used in here? This is the least square approximation, which means that we reduce the mean square error by using the what using these algorithms. Okay, and so x stacked transpose x next transpose and r count should be given in here. Okay, so after this algorithm is run, a estimate is assigned AB estimate 2 and the whole data transpose T, and the B estimate is obtained with what the last two data transpose values. Okay, and after that we should print the what the true a matrix, print a true, and we should give the what the true B matrix in here, and after that we should give the what the estimated matrices. Okay, A estimate, and B estimate. You don't know anything about the linear programming or the least square approximation, but in the next session or in the next year you will learn about how you can utilize the system dynamics or the dynamic implementation of your system. Okay, but in that case or in this lesson, which is given in the in the next year, and you will always utilize this solution for a given data. Okay, and so if I run this code and then we have the true A matrix 0.5 minus 0.2, 0.5, 0.2, and 0.8, 0.1, 0.8, 0.1, and the true B matrix 3, 2, 3, 2 are given. Okay, and so we can estimate the whole values by using these terms. Okay, so the emulation of your fitting data can be given in here. Okay, firstly we need to create the X estimate values with the 0 value in here, like this one. 2 is the dimension of these terms, and the time steps is the number of this vector. Okay, and for T in range 1, 2 time steps. Okay, and X estimate can be updated with the T values in the MP dot, and A estimate, X estimate, the whole row data, and the T1, T minus 1 column data. Okay, and also we should give the MP dot, B estimate, U, T minus 1. Okay, so how can we calculate the error values? Error can be assigned with the X next minus X estimate with the 1 to infinity. Okay, so how can we create the figure to show the representation in here? Firstly, we need to define the plot figure in here. Fixed size is the 10 and 6, and PLT subplot can be given in here like this one row 3 column and first operation. PLT plot MP range is the time steps minus 1 times dt which is equal to R seconds in here, because we have the sampling rate at the dt, and then we can create the 0 to time steps array, and if we multiply these terms, and then we get the total second time. Okay, and X next 0 label true, X1 can be given in here, and line style should be given in here like this one. The marker is the O. Okay, so can generate the X next 1, 2, and also we should give the plot X label as a time, and Y state value, and title true state trajectories. Okay, and also we should give the PLT legend. Okay, in the next case we should copy of the whole of these things and 2, but in this case we should give the X estimate, okay, and this is the estimated X1, estimated X2, estimated state trajectory, and also we need to give the residuals of these terms. Okay, and so the error must be given in here, error, and the error, and error. Okay, so after that we should give the tight layout formulation, and PLT show must be given in here. we have the sum error in here, time steps -1. Here x estimate 0. Okay. In the x estimate we have error, and we analyze the terms in here, time steps and a estimate t -1. Okay, and b estimate t -1. Okay, and so this is the x next, x estimate. Okay, this error is true, and also should give the what, the -1 total data 1.1, and this terms is 1. Okay, and 2. Okay, true. So we don't have any error in here, but in the range of these terms, MP full time steps is also true. Okay, but the x and y must have this dimension on. Okay, xt x estimate MP zeros 2 time steps. Okay, in these terms x estimate. Okay, estimate -1, b estimate 2 minus t1. Okay, it's true. MP arrange time steps -1 dt, and I'm sorry. This is given in the what, this the first term is the initial condition. I have this error in here. Okay, so if I rerun this code, and then we will have the true and estimated and the error state trajectories. In the orange line is the true x2. It's a dynamic system, but the estimated state trajectory, this one. Okay, and this is the what, the blue line, and so we have the smaller error trajectories in here. Okay, so how can we add some random error in here? Rand n, for example, 2, 1. Okay, so if I run this code, could I say should 2 2? I'm sorry. 1 2 2 1. I think. Okay, but it's the highest values in here, rand n. Okay, so we need to divide 2 in here like this one, and so we don't have the estimated error, not enough. Then it's not good enough. $1,000 for the random values. It's not good enough. It's much higher values. It's not good enough. The error is higher now, and this terms is also given here. There are some errors in the x utilization in here, so we can print these values in here. Firstly, can analyze the whole values like this one. Okay, so this is the 1 and 0. It's the all cases. It's not good enough for us to what? We should convert to the float values in here, and so all the scalar values must be used in here, and then we should create we don't need to apply this error. Okay, but in this case, okay, so if we add the sum generated noise in here, this is not good enough. Okay. And so we have the some noises values in here, like this one. Okay. But the R estimation is correct. But in this case, just remember that 0.3 true B matrix, but in our application 0.3 and 1 is estimated because we have the noises value in here. But in the estimated state trajectories, we have the different values in here. For example, if I set the 50 values in here, and so we have the higher noises value. And so our B matrix and A matrix is also changed in here in order to minimize the R approach. Or we can change the 25 in here, and then the R matrices are going to the different values. For example, this is the 0.5, but 0.52 is obtained in here. For example, if I choose the 15 values in here, the higher noises is applied to the system, and then the R matrices, estimated matrices, is converging to another values. But in order to minimize the R noises in here. Okay. Firstly, so we have the 5 values in here, like this one, and so we may have another representation because the true A matrix 0.5, but the R matrix is contained with 0.04 increased values in in our application. Okay. So that's the end of this lesson. In the next weeks, we will continue with the curve fitting techniques in Python approach or Python programming language. I hope you have learned everything about what I'm saying in this lesson, and so have a good day.